Hello and welcome to this video on single loop circuits. In this video we'll describe how to do the analysis of a single loop circuit, and in the process we'll come up with another useful formula called the voltage divider. So let's begin. Suppose that we have a circuit that looks like this. We'll have a source, and we'll arbitrarily set this at 48 volts. We'll have a resistor, which we'll set at 1 ohm. Over here we'll have another resistor, which we'll set at 10 ohms, and another source, which we'll say is 30 volts. So, as you can see, this circuit has a single loop. If I draw around this loop, it looks like this. Another way of talking about this is to say that all of the circuit elements are in series with each other. A series connection means that all of the current that flows through one element must flow through the next element. So for example, the 1 ohm resistor, all of the current that flows through this 1 ohm resistor, say like this, must flow through the 10 ohm resistor because they're connected and there's no other place that the current can go. Similarly, all of the current that flows through the 10 ohm resistor flows through the 30 volt source and through the 48 volt source. So this is a series connection. Okay. What we would like to do is find out what the current is that flows around this loop. So our goal is to solve for I. It turns out that once we know the current that flows through the loop, then we can easily find the voltages across the two resistors as well. Okay, so the approach we're going to use is we'll apply Kirchhoff's voltage law around the loop that I've drawn here in green. Now, to apply Kirchhoff's voltage law, we need to express the voltage across each resistor. So let's do that first with this 1 ohm resistor. If the current flowing through that 1 ohm resistor is I, and again I will be the current that flows through every element in this loop because they're in series, then the voltage of the 1 ohm resistor, I guess we can write it like this, V sub 1 ohm, is the current times 1 ohm. So the way we've drawn the current, that says then that this is going to be V sub 1 ohm. The voltage for the 10 ohm resistor, for this guy here, is going to be V10 ohm. It will be the current flowing through the resistor, which is I, times 10 ohms. So basically, this will be V10 ohms. Now you'll notice that I'm drawing these voltages so that the current in the resistor, or through the resistor, is flowing from a higher potential to a lower potential. So again, in this case, the current is here. It flows from this point, which is a higher potential, to a lower potential. In the case of the 1 ohm resistor, I have the current flowing up. It's going up this direction, and again I've marked it so it's flowing from the higher potential to the lower potential. So knowing what knowing the voltages now across the resistors, the thing that I don't know in each case is I, but we'll solve for that in just a minute. I can now apply Kirchhoff's voltage law around the loop, and let's start right here with the 48 volt source, we're going from negative to positive, so applying Kirchhoff's voltage law, I have negative 48 volts. Then in the 1 ohm resistor, we're going from positive to negative, plus V1 ohm plus V10 ohms plus 30 volts. Okay, so here I'm going from positive to negative through that source is equal to 0. Okay, now I'll do a little bit of math. I'll move this guy and this guy to the other side of the equal sign. So I have V1 ohm plus V10 ohms is equal to 48 volts minus 30 volts. Okay, now I can plug in my expression for V1 ohm. This is I times 1 ohm. And my expression for V10 ohms, this is I times 10 ohms. And this other part stays the same. Okay, now I have an I here and an I here. I can factor both of those I's out to give me I times 1 ohm plus 10 ohms. And again, this is still equal to 48 minus 30 volts. And finally, to solve for I take, left out my volts there. I divide both sides by 1 ohm plus 10 ohms. And if I do that, let's see, I'm sort of running out of space on the bottom, so we'll put it up here. I'll sort of highlight this as a very important result. I is equal to 48 volts minus 30 volts over 1 ohm plus 10 ohms. And so now I can actually work this out. If I do the computations, I have 48 minus 30, which would be 18, divided by 1 plus 10, which would be 11. That gives me that I is equal to 1.636 amps. Okay, so there's my answer. Now, it turns out that there's a couple of interesting things to point out here. One, well, actually the most interesting thing and the most useful thing is you'll notice that I have here 48 volts. That corresponds to this source. 30 volts corresponds to this source. And then 1 ohms corresponds to this resistor, and 10 ohms corresponds to this resistor. So what I actually have here is on the top, I have the algebraic sum of the voltage sources, and on the bottom I have the sum of the resistors, or actually the sum of the resistances. Okay, and this is a pattern that you'll see generally in single loop circuits. Okay, so having computed I can now go back and compute the voltage across the 1 ohm resistor. So V1 ohm is going to be I times 1. So this is going to be 1.636 volts. V10 ohms is going to be I times 10, so this is going to be 16.36 volts. Okay, so that's pretty much everything we can compute in this circuit, and we've done it by, again, starting at some arbitrary point in the circuit, going all the way around the loop, applying KVL, and then solving for the current. Okay, again, this technique applies whenever you have voltage sources like this and like this in series with resistors. So I think we'll let that be the end of this video. Again, this is the single loop circuits. Thanks for watching.